electron energy, and it's just the momentum, or this is a quasi-momentum, so it's Planck's constant over 2 pi times k, the wave vector, squared over 2m star. So this is just like almost a free electron. M star is the effective mass because the electrons are in a solid rather than a vacuum. And we're going to keep this isotropic. It's going to be the same energy whether the k vector is pointing in any direction. But the important point is that the wave vector is quantized. So the energy states are like points in k space. So here's a diagram. These little blobs here are the allowed energy states as a function of kx, kz, and ky. And electrons are fermions. That's something I alluded to in the introduction. That means that only one electron is allowed in each quantum state. But we also have to remember that the quantum state isn't just defined by motion, it's also defined by spin. So electrons have spin half, which can point up or down, and each energy state holds then 2 electrons, one with a spin pointing up, one with a spin pointing down. So what we'd do if we were kind of making a metal from scratch would be that we put 2 electrons in here, 2 electrons in here, 2 electrons in all of these states, and gradually, as we filled them up, we'd have to go to higher and higher energies. So we'd start at the lowest energy until all of the electrons are accommodated. And when they're all in the solid, they will make a kind of surface at absolute 0 temperature, which I've shown in this purple color here. This separates the full and empty states. Excuse me. And this thing is known as the Fermi surface. And the energy at the Fermi surface is known as the Fermi energy E sub f. So those are going to be important things that we're going to have to remember. So just here we are, textbook stuff to remember. The Fermi surface is the constant energy surface which at 0 temperature separates the occupied states from the empty states in momentum space. If we know the size and shape of a metal's Fermi surface, we can understand how its free electrons behave, and hence we can account for a lot of the properties. For instance, if you know the Fermi surface, you can predict the metal's bulk modulus quite effectively. So the Fermi surface is a consequence of Fermi-Dirac statistics, and a metal, as I said, for conventional purposes, is a solid with a Fermi surface. Of course, in real metals, the energy is a more complicated function of the wave vector than the one I gave you earlier. In real metals, the atomic orbitals result in a much more complicated dependence of electron energy on wave vector. Here's one I looked at recently. This is the topological material, gold beryllium. And you can see the bands are going up and down, they're crossing the Fermi energy. And so if you can imagine that as a function of K space, it is making all sorts of little pockets and things. So Fermi surfaces in general are not spherical. So here's some examples. Copper is almost spherical, but it's got these little sort of blobs that reach out to the boundaries of the unit cell in K space, the Brillouin zone. Chromium has got this weird thing like a sort of top in the middle of it, and then lots of blobs on the outside. Vanadium's even worse. And yttrium is what's known as a monster to Fermi surface specialists. So you can see that they do deviate from being spheres in real life. Anyway, here's going to be an important consequence of Fermi surfaces, and these are magnetic quantum oscillations. Now, the motion of electrons once they're in a solid is governed by an equation of motion that looks really like free electrons, except there's some subtle differences. First of all, we deal with the wave vector k rather than momentum. So when we say the Lorentz force, we've got the rate of change of wave vector over here is given by the force on the electrons. And because we've got a quantum mechanical particle, the electron velocity is in analogousness to your d omega dk for the group velocity in one dimension. The velocity is given by the gradient in k space of the energy as a function of k. So we can put those things into the Lorentz equation. You can see automatically the force is going to be perpendicular to the velocity, which means that it's along a surface of constant energy, because the velocity points outward. So here's a Fermi surface. This sort of wiggly thing here is a model Fermi surface. The arrows are the velocity vectors of the electrons, these red arrows, and they're pointing out perpendicular to the Fermi surface because the Fermi surface is a constant energy surface, and this is the gradient in K space. And then we've got the velocity crossed with magnetic field. So the orbit is perpendicular to those velocities, and it's perpendicular to the magnetic field. So you get the electrons going round and round and round in a circle on the Fermi surface, and they describe an orbit which has got a cross-sectional area S. Now, this is all kind of a bit classical mechanics-y. In fact, of course, quantum mechanics rears its head, and these orbits are actually quantized. So the energy as a function of magnetic field is given by this expression, proportional to magnetic field, the effective mass on the bottom. There's a quantum number here, a phase. This has become very interesting over the last 10 years because of Berry phases. And then because the force is always in a direction perpendicular to the magnetic field, the motion along the magnetic field direction is not affected. Anyway, these levels are called Landau levels. They're called Landau levels. And even though they're called Landau levels, the person who worked out most of the theory is this guy here, Ilya Lifshitz. And we'll hear his name quite a bit more as we go through this talk. So every time a Landau level pops through the Fermi energy, we get an oscillation in properties like this oscillation in the resistance here of a high temperature superconductor. And these oscillations are periodic in 1 over magnetic field. You can imagine if you make this energy up here, the Landau level energy equal to the Fermi energy, every time you increase this number by 1, the field is going to go down equally in 1 over b. So these oscillations are periodic in 1 over the magnetic field. And their frequency, therefore, is like a field. It's in Tesla, and it turns out to be proportional, directly related only by fundamental constants to this area of this orbit here. So this is a very useful technique because we can actually map the surface of the shape of the Fermi surface out by looking at the frequencies of these oscillations. So because they're periodic in 1 over b, in what's going to come, I'm going to often plot things like oscillation positions and things like that versus 1 over b or 1 over h. So don't get surprised by that. It makes everything periodic. Now, we come on to a test for fermions. So electrons are fermions. They obey Fermi-Dirac distribution function. And this is written here. You're probably all familiar with it from thermodynamics classes and things like that. It gives the probability that a state of energy E, energy here, is occupied at a temperature T. So if we make it absolute 0, what happens is that this expression goes along 1, and then suddenly when it gets to mu, the chemical potential, it falls vertically, and then it's 0. And of course, then remembering back the diagram of the Fermi energy, at T equals 0, the chemical potential equals the Fermi energy. So now we put the temperature up, and what happens is the Fermi-Dirac distribution function gets kind of smeared out over a region that's about the Boltzmann constant times the temperature wide here. So it's no longer perfectly sharp. So what happens is the Landau levels are passing through a blurry Fermi surface rather than a sharp one. And so the oscillations get smaller. And here's some example data from about 12 years ago that I took on an organic superconductor at various different temperatures. The lowest one, 620 millikelvin to 1.34 Kelvin. And what you can see is here are the oscillations, periodic in 1 over magnetic field, and they're getting smaller and smaller and smaller as the temperature rises. And this is just due to this Fermi-Dirac distribution function getting rounded out here. So if the oscillations are due to fermions, then their temperature-dependent amplitude is solely due to this Fermi-Dirac statistics here. And Lifshitz, who you saw on the previous slide, he derived an expression that describes this. It's essentially just the differential of the Fermi-Dirac distribution function, and the amplitude of these oscillations goes like this, with chi equal to 14.69 times the effective mass times the temperature over the magnetic field, as long as you use SI units. So let's just revise consequences of having Fermi surface filled with fermions. So we already heard about quantum oscillations, the de Haas van Alphen oscillations are those oscillations periodic in 1 over b in the magnetization. The Shubnikov-de Haas oscillations are oscillations in resistivity, and they are due to the Landau levels on the Fermi surface. Also, because of the way in which the statistics works, the electrical resistivity falls as the temperature decreases if we have a metal. And at low temperatures, we have a heat capacity due to these fermions, these electrons, which is proportional to the temperature. And also at low temperatures, a thermal conductivity that's proportional to the temperature. And Pei Chun mentioned my textbook at the beginning, so here's a piece of shameless advertising, but you could also use Ashcroft and Mermin to revise these things. So now we've done conventional metals, we're going to move on to the weird materials. And there's a note to start with. Here we go. Ytterbium dodecaboride is fairly non-magnetic. So I'm going to use mu naught H, which is the applied magnetic field that we apply to the substance, and the magnetic flux density, which is the force, which gives the force felt by the electrons, rather interchangeably. Because m is small, these things are more or less equal to each other. And they're both in Tesla. If you need help, see a magnetism textbook. Okay, here we are, the condo insulator, ytterbium dodecaboride. And here's two different views of the structure. I thought I'd show this one, which shows all of the atoms in the face center cubic unit cell. It looks rather a mess. So what I've done here is I've just got another view of it, which just shows two lots of the cluster of berylliums around, borons around the ytterbium. So each ytterbium has one of these dodecahedra around it, and these are all of the boron atoms here. So anyway, this material, you can put electrical contacts on it. And so with a couple of samples, here are some results that we got earlier a couple of years ago. Here's the resistivity, here's the temperature. And what you notice straight away is that the resistance is going up as the temperature goes down. And that's exactly the opposite of what I told you for a metal. So it's really an insulator. It is not a metal. So this is what's going on. It's a condo insulator. So what we have is we have localized states which are magnetic, and they have just a monoenergetic energy level like this. And then the conduction band in which the electrons are trying to move around goes through them. So what happens is there's interaction, hybridization, and what that leaves is a band gap. It opens up an anti-crossing here, so that you get a sort of band up here, and then you get band down here as well. And the dotted line shows you what the situation was like before. So we now have the Fermi energy will usually be pinned to this set of localized states. So there's no mobile states at the Fermi energy. The electrons are all in here, and there are no electrons up here. So that's why the resistance tears off. It does a slightly strange thing at low temperature, which one of you can ask me a question about at the end. But in general, things like this, the resistivity is given by a band gap divided by the temperature, e to the power of this. And this shows that there's a little kink here and here. So the band gap sort of spends some time opening up until it settled down to a low temperature value. But basically, it's a condo insulator. There's a band gap there, and that makes it into an insulator. So now we look at some experimental data. And here's the resistance or resistivity of various different magnetic fields as a function of temperature. And what you can see is up to 45 Tesla, the resistance is still increasing as you go down in temperature. So it's still behaving like an insulator. So it stays an insulator up until about 45 Tesla. And then the band gap on the previous page, this thing here, closes. So now here we have the resistivity plotted as a function of magnetic field. You can see it's big here, then suddenly it goes crash, and there's very little resistance left. This is an enlargement of here. So the resistance is almost field dependent above here, and it's very, very small. So it looks like a metal, and this is actually what's called a condo metal. But here's the interesting thing. There are oscillations in the resistance that are showing up while it's still in the insulating phase. And they seem to be periodic in 1/b, in 1 magnetic field. That makes them really like leading suspects to be quantum oscillations, but in an insulator. So what we had to do was check using another measurement. So as well as the pulse field measurements, we went to the Tallahassee 45 Tesla hybrid magnet and put the sample on the torque magnetometer. So the torque magnetometer is like a capacitor, and the top electrode of it is a spring, and the sample sits on top of this spring. You can see a picture of it here. There's the sample, and here's the place where it sits, and then the capacitor lower plate is down here. And as the sample experiences different forces, which are given by its magnetic moment crossed with the magnetic field, it goes up and down, and that varies the capacitance. So you can make quite a good measurement of magnetization using this. Why is it important to look at magnetization? Well, magnetization is a thermodynamic function of state. That means with essentially no assumptions, you can relate it to the microscopic electronic free energy. So if you see stuff in the magnetizations, then it's got to be a real effect of the electronic energy levels. So here we are. Here's the picture. Function of magnetic field on the bottom here. This was at a temperature of 350 millikelvin. It's for the torque magnetometer at two different angles in the magnetic field, as defined over here. And you can see that there's a signal, and then the oscillations, just like we saw in the resistivity, start up at fields of above about 35 Tesla. So there are oscillations in the magnetization. They're periodic in 1 over magnetic field. They are pretty certain evidence for LANL levels. But let me remind you, it's an insulator. So these are metallic looking properties happening in something that's an insulator. So are these magnetization oscillations due to fermions? Well, you remember the Lifshitz-Kasiewicz formula after this guy Lifshitz that I showed you the photograph of, where we could say that the amplitude of the oscillations was this function here in SI units. That means temperature in Kelvin, not Fahrenheit, and B in magnetic field, not in Tesla, not Gauss. And so we can fit this to the amplitude of these oscillations as a function of temperature. And here we have the data are dots, and the red line is the Lifshitz-Kasiewicz formula. So basically, it's an excellent fit. So the oscillations are virtually surefire due to fermions. They're almost certainly due to fermions with a Fermi surface. And of course, we can know its size because we have the frequency of the oscillations, which is like its cross-sectional area, and we have the effective mass from doing this fit. So we know a lot about this Fermi surface already. So now let's go to other properties. And if you got fermions, then they have a very, very distinctive effect on the heat capacity. So the fermion contribution to heat capacity, because of the Fermi surface, at low temperatures is given by this constant gamma, which is known as the Sommerfeld constant, times the temperature T. Now, phonon and other contributions give you different power laws. It can be a T cubed, it can be exponential, and there can be other things like Schottky anomalies and stuff like that. So if we collect these together, you get an expression for the heat capacity divided by the temperature, which is a constant plus all of these other contributions. So in this particular case, the contributions are quite simple. There's a phonon contribution due to Debye-Einstein phonons, and then there's a Schottky anomaly contribution as well. So gamma should be given by just looking at this. So here are the experimental data. This is the heat capacity divided by the temperature. This is the temperature here. Experimental data for 2 different samples with the different colored, different red points here. This is the phonon and the Schottky anomaly contributions added together. And if we look at this, the difference between them is constant. So we are coming out with a gamma that is a constant, which means that it's a pretty good indication that they're fermions. So if we plot that gamma as a function of temperature, you see it's turning out as a constant, and it's the same for the 2 samples. And we can also model this. If you go back to if you go back to a solid state physics textbook, you can model this, and we have the quantum oscillations, and basically the Fermi surface quantum oscillations and size are consistent with this size of the heat capacity contribution for fermions. So it really does look like we've got things that are behaving in many ways like electrons, but they're not conducting electricity. So we can also look at the thermal conductivity. This is a bit more complicated diagram because it was done at lots of different magnetic fields, but basically the same thing is happening here. It's a similar idea to the heat capacity. The fermion contribution is proportional to the temperature. the phonon contribution to the heat capacity is proportional to T cubed. And so if we plot the thermal conductivity divided by temperature, we will get the electron contribution will come out as a constant, and then we will get this AT squared here. So this will turn out to be an intercept, because the T will just divide out the T that's in the upper place. And you can see, indeed, these things have finite intercepts here. And if we work it out as a function of field, you can see that these are constants as a function of field, and they're of a similar order of magnitude to each other. So the finite intercept shows that there's again a contribution due to fermions. And this size here is consistent with the parameters deduced from quantum oscillations. And so these things are all telling us that this material is filled with a load of things that look like electrons, behave like electrons, but don't conduct electricity. So let's summarize that, because it's very important. We have strong, consistent evidence for itinerant, that means mobile, fermions in ytterbium dodecaboride. There are quantum oscillations in the magnetization and the resistivity. That means that you got something that looks damn like a Fermi surface. You got heat capacity that looks like fermions. You got thermal conductivity that looks like fermions. But they're not normal free electrons because they don't carry charge. So what could they be? Well, a distinct possibility is Majorana fermions. And Italian physicist Ettore Majorana suggested, it's a long time ago, getting on for 85 years ago, that neutral spin half particles could be described by a real wave equation. And if it's real, it means that the particle is identical to the antiparticle. And those of you who've done this sort of advanced quantum mechanics, you'll realize this, because wave functions of particles and antiparticles are related by complex conjugation. So in other words, if it's real, they must be the same. As I say, this is quite a subject in particle physics at the moment, because there's arguments about whether neutrinos are Dirac or Majorana fermions. So the thing is, these must be neutral, but there might be a possibility of making them from some sort of superposition of positive and negative charges. And so they could perhaps interact with a magnetic field. So how could this happen? Well, the answer is it could happen if you read this paper down here, which is about 40 pages long, with about 300 equations in it. So I'm not going to take you through all of that, and I'm an experimentalist anyway, but I'll give you a kind of hand-waving argument as to why this might happen in ytterbium dodecaboride. So ytterbium dodecaboride is a mixed valence system. So mixed valence systems are solids where you can have ions, and I'm going to label them X just as a model thing, and their normal charge, you know, can be Xn plus, say 3 plus or 4 plus or something, but the valence of these charges can change. That's why they're called mixed valence systems. Some of these things you look and you have an equal population of, say, 3 plus and 4 plus. Some of them, the valence kind of fluctuates and hovers around some even non-integer value like 3.5 or something. So let's have a look what consequence this might have. Remember, this is an insulator, so we're trying to maintain charge neutrality. So let's start if we have n plus 1 minus state, sorry, that should be plus here. Let me just change that. Sorry, it's confusing. There we go. Oops, no, not quite. Right, go back to the presentation. Yeah, so we have n plus 1 plus here. That means we've deviated by 1 charge from the neutral situation. So that means to compensate, we have to have a free electron that's roaming around in the solid just to keep charge neutrality. Let's see if we charge the charge state down to n minus 1 plus, then we've removed an electron from the solid. So we made a hole which behaves like a positive mobile particle. So you can see by making the valence go up and down, by changing the number of pluses on this X ion, you can make mobile charge carriers, which are there to compensate to make the thing electrically neutral. So we can produce things that are positively charged or negatively charged in the solid. Now we do an epic hand wave, which accounts for about 300 equations in this particle. So we let, in this paper rather, we let the charge state of X fluctuate between n minus r, and this can be quite a small thing, plus, and n plus r plus. So the free fermions that are created, if this thing is fluctuating, if it's wobbling around really, really fast, is some sort of superposition of electrons and holes. So there would be overall charge neutrality, very little conductivity, but nevertheless, there may be some entities that look like mobile fermions. They could have a free energy and carry heat. Now, in a way, you can regard an electron and a hole as being like a solid state particle and antiparticle. What we've got here, because you've got this fluctuating thing, is you've got something that looks like it's a mixture of both. So it's looking rather like a Majorana fermion. So what about the interactions? Well, I'm going to quote from this paper, which anyone who wants to read about this and theorize on it should read. So Majoranas crossing the chemical potential are linear equal combination of a canonical particle and antiparticle operators. The linear coupling to a vector potential A changes their energy to this. Now, let me remind you what a vector potential is. The magnetic field is given by curl of A, and the electric field is given by the time differential of A down here. Any electromagnetism textbook will tell you that. So you can see we've got two energy terms here, and they're equal and opposite in A. If we take the time differential of this, there'll be a dA by dt comes into here, and there'll be an exactly opposite one comes into here. So the linear response to A, for example, electrical conductivity, is then 0, but effects quadratic in A are present. So why would effects in quadratic in A be present? Well, if you go through any condensed matter physics textbook like Ashcroft and Mermin or mine, you will find that the response of fermions that are charged to magnetic field is like a harmonic oscillator potential, and it goes like the magnetic field squared. So basically, if we have a magnetic field, these things are like the magnetic vector potential squared. So the magnetic oscillations are effects due to changes in free energy, which are functions of even powers of the magnetic field. So, says Chandravarma, we have the same oscillations as in the customary theory. In other words, even though these things don't respond to an electric field, which is linear in A, in things that are like squares of the magnetic vector potential, they respond just the same as other fermions. So we can get quantum oscillations. So now what we're going to do is we're going to look and see what happens to these Majorana fermions, if that's what they are, as we go into this metallic state up here. If you remember, we have a band gap down here, which makes it into an insulator. And then as we increase the magnetic field, the band gap finally closes, and we have this very, very low resistivity here. So what do we know about this state already? Well, we're not the only people doing measurements on this. So some people in Tokyo did pulsed field heat capacity measurements. And up here, it shows that there are so-called heavy fermions, electrons with an effective mass of 100 times the mass of a free electron. I mean, this is sort of well-known physics. The Kondo effect can give heavy fermions, so heavy electrons, and they're charged. They move a bit like conventional electrons. They just look as though they're very heavy. So they're up here. Also, the conductivity is very high, so it looks like a metal. So again, it looks like these electrons, although they're heavy, are moving like normal. They have charge, and they're behaving themselves. So our transition is actually from a Kondo insulator to a Kondo metal or heavy fermion phase at 45 Tesla. So what can we do to look at this state? Well, one of the things that we did was a thing called a proximity detector oscillation method, which is something that Pei, Chun, and I have used a lot in the past as well. So this is a way of measuring the conductivity in something that's got a very high conductivity, and it's difficult to make contacts to it. And so you wrap a coil of copper wire around it, and this is very narrow copper wire. It's 50 gauge wire, so it's like a human hair. It's set up on a platform that tilts in the magnetic field. So the sample is this silver thing inside the coil. Now this is connected to an oscillator, which is a floppy oscillator. The proximity detector oscillators are used in metal detectors, and these things free oscillate between 20 and 30 megahertz, and the frequency of oscillations is given by a tank circuit, of which this is the inductance. So changes in sample conductivity shift the coil inductance, and that gives you a change in resonant frequency. So we just measure the frequency versus the magnetic field, and changes in skin depth of the sample, which is the amount of penetration that you get of oscillating fields, will go like this. So the conductivity is, the skin depth is in the conductivity. So if you get changes in conductivity, you get changes in skin depth, you get changes in frequency. So you can get out something that looks like a conductivity versus magnetic field. So this method is sensitive to skin depth and to a lesser extent susceptibility. Now, in the insulating state, we know we have a good insulator because the oscillating fields from the coil completely penetrate the sample, and there's nothing happening. Then we go through the metal to the insulator to metal phase transition. Now we get a response as the sample acquires a big conductivity and a small skin depth, and it takes off. We see this response, which is like magnetoresistance, and we see these quantum oscillations on top of it. So we've got a signature of the phase transition from insulator to metal. We got something that looked like quantum oscillations in the metallic phase, in the condo metal phase. So here's those oscillations. We get them by fitting a function to the background shape of these curves here, and then what's left of these oscillations. And this is again plotted as 1 over magnetic field. And notice now that the oscillations are turning out not quite periodic in 1 over magnetic field. So going back to the condo insulator that I showed you earlier, we had these oscillations in the resistivity and the torque. If you allocate a number to them and then plot that number against 1 over magnetic field, you get a straight line because they're periodic in 1 over magnetic field. Now, if we go into the condo metal phase, these things are no longer periodic in 1 over magnetic field. They describe this curved line here. So what's going on? Well, we struggled around looking for a way of making these things fit. And finally, we came on a function like this. So this is the positions of those quantum oscillations in the condo metal phase, these things here, for different angles of the magnetic field. And then they're plotted against 1 over not the magnetic field, but the magnetic field with an offset. And you can see now they go back onto being lying on straight lines. So something is happening. Something is causing this frequency of the oscillations to change as a function of magnetic field. While we're here, we should remark that the quantum oscillations still fit this Lifshitz-Kotsievich formula. And that means that we got fermions causing the quantum oscillations in the condo metal state. So the oscillation amplitudes fit the temperature-dependent part of this Lifshitz-Kotsievich formula, and that means that we got fermions. So what's going on? Well, actually, what's happening is the frequency of the oscillations is changing with field. And so we can parameterize this relation up here by putting in a function that looks like this. This is the frequency. Now it's a function of magnetic field. And that means that the area of the Fermi surface is a function of magnetic field. And so the Fermi surface is changing with field. And this is what the area is doing. So what's happening is we can then use this function to plot what's happening to the field, the frequency as a function of magnetic field. You can see it's going down and down and down like this. But then if we extrapolate it backwards, it links up with the frequency of the quantum oscillations in the condo insulator phase. So in other words, it very strongly suggests that the same Fermi surface is responsible for the quantum oscillations in the insulating phase and in the metallic phase. But something is happening to it as you go to the condo metal phase that's making the frequency die away. That means that the Fermi surface is depopulating. It's becoming smaller and smaller as you go to a high magnetic field. So it's just pootling along with a constant frequency, constant size here. Suddenly it hits the condo metal phase and it starts dying, and its fermions are abandoning ship and going away here. So just to summarize that, because it's an important point, the back extrapolation of the quantum oscillation frequency in the condo metal state seems to link up with the one in the condo insulator state. So the inference of this is that the Fermi surface detected is the same as the one in the condo-insulator phase. Now, we of course attributed that condo-insulator phase Fermi surface to neutral fermions. Are they still neutral in the condo-metal phase? And why is the Fermi surface depopulating, as evidenced by the frequency going down as the field increases? To understand these things, we need to measure the conductivity in the condo-metal phase properly. So you remember that the condo-metal phase had this very, very low resistivity. So if we're going to put a big current through here to measure it, a problem would be that in the condo-insulator phase, we'd probably blow the sample up or blow the contacts off or create an enormous signal which would saturate the amplifier. So what we do is we set up this system over here on the right of the figure. This is triggered by the magnet, and we have a clever function generator that generates a couple of pulses that turns on the current just above 47 Tesla. So here's the field pulse in our pulse magnets. Here's the magnetic field on this left-hand axis. On the right-hand axis is the current, and here's the time. So what we do is we turn on the current, and it's about 2 milliamps, 2 and a bit milliamps, just when the field is above 47 Tesla. So we're measuring the resistance only in this part. So we can use very, very sensitive amplifiers, pretty sure that they won't get blown up by an enormous signal back in the insulator phase. It also avoids sample heating. So now we can get the resistivity. So it's just to keep to time, there's very little magnetoresistance, so I'm going to just plot the values at 55 Tesla. So the quasi-particles, straight away that we can see, the quasi-particles that give quantum oscillations play a very small part in the conductivity. Why can I say this? Well, there is very little magnetoresistance. So let's have a look. If the magnetoresistance in the high field condo metal phase were due to these quantum oscillation producing particles, it would be very field dependent. For a start, we have the frequency, which is going down as the field goes up, which means that there are less and less of these things as we go to high fields. So the resistance should go up. Also, the effective mass is changing as a function of field, which I got from those fits back there. So the resistivity would be really, really quite field dependent in this condo metal phase if it was due to the same fermions that are giving the quantum oscillations. The resistivity that we actually observe is almost field independent, and there are no quantum oscillations in it. So basically, whatever is causing the resistivity is not predominantly the fermions that give the quantum oscillations. So the quasi-particles that give the quantum oscillations play a very small part in the conductivity. Also, this absence of magnetoresistance means that there's very little disorder. So this conductivity in the high field phase is dominated by this large Fermi surface of heavy electrons that was suggested by the pulse field heat capacity data that I was talking about earlier. And so what we can do is look at how this is behaving. If you look at very low temperatures, this is the resistivity at 55 Tesla as a function of temperature, you can see that it looks like a parabola down here. And we get that if we plot the resistivity as a function of T squared, it lies on a straight line. Now, this is the expected behavior for heavy electrons, like the heavy fermions that we're expecting in a condo metal. So in a way, no surprise there. But then it goes over to being linear at higher temperatures. And linear magnetoresistance, linear in temperature, is characteristic of a so-called strange metals. So that's another clue as to what might be going on here. So let's summarize. The condo metal has a large Fermi surface sections of charge-carrying electrons, and these dominate the resistivity and the thermal properties. However, their masses are very heavy. We can estimate from the heat capacity that they're about 100 times the mass of a free electron, and so they're not going to give us quantum oscillations. However, we get quantum oscillations, and I think that they're due to neutral fermions, but their frequency is now field independent. So what we're proposing is in the high field condo metal phase, we have an additional fermion reservoir, which is the condo metal Fermi surface of conventional heavy electrons, and it's not present in the low field phase. It's now existing in the condo metal phase. So the neutral fermions Now, maybe there's somewhere that they'd like to be. They'd rather be charged fermions in a conventional Fermi surface. So they start to depopulate their Fermi surface, and that gives us the field-dependent quantum oscillation frequency. So why are we still confident that there might be neutral fermions around? Well, there's a recent theory which describes the linear temperature dependence of bad metals. And this can only come from the presence of two quasiparticle or two fermion reservoirs, one of which is electrically inactive and the other of which has a conventional Fermi surface. And you get scattering between them, you get transfer of fermions between them. And that's the only way you can get a linear T resistivity. So this is very strongly suggesting that we have these conventional electrons that are very heavy, and then we have the neutral fermions, which are still hanging on in their Fermi surface from the low field phase, but it's gradually getting destroyed. So let me put it like this. This is rather like a two-fluid picture. The properties of ytterbium dodecaboride can perhaps be understood in terms of the following. So in the low field conduit-insulator phase, we have a low density of charge-carrying electrons, and they're caused by excitation across the gap, and they're cohabiting with the Fermi surface of neutral fermions. And these two exchange fermions via low energy scattering. In the high field conduit metal phase, we also have cohabitation. A Fermi surface of heavy electrons cohabits with the Fermi surface of neutral fermions, and the two exchange quasiparticles via low energy scattering, and that gives you this T linear resistivity. But as you raise the field, the neutral fermions are no longer entirely happy about being neutral fermions, and they're gradually depopulating into the conventional Fermi surface as the field rises. So that's a picture that kind of accounts for our results. There's one thing left to understand. Why are there quantum oscillations in the resistance in the conduit insulator phase and in the PDO signal, which is a skin depth measurement in the conduit metal phase? So even in conventional metals, quantum oscillations in resistivity are very hard to model. And you can see the canonical textbook for this, Schoenberg. And it's all down to a suggestion by Schoenberg's colleague Pippard. The rate of quasiparticle scattering is proportional to the density of states available for scattering into. Just a Fermi golden rule argument. So if there's a high density of states, you'll get a lot of scattering, you get a high resistance. If you have a low density of states, you have not very much density of states to scatter into, so you get a lower resistance. So in a Landau level system, which I've shown on the left of the diagram, as the Landau levels go up towards the Fermi energy, the density of states will oscillate, therefore the amount of scattering will oscillate, and therefore the resistivity will oscillate. Now we have a similar sort of argument in the conduit insulator phase, but this time the charge is being carried just by the dilute electron gas, which is due to excitation across the band gap and some mid-gap states which give you that saturation. So what's happening is you're getting scattering between the neutral fermions, which have Landau levels, and these dilute electron gases. So the scattering will get big when the density of states in the Landau level density of states is large. It will get small when it's like this. So the amount of scattering will oscillate, and you will get an oscillation in the resistance. The resistance is being solely provided by the dilute electron gas, but its scattering is being modified by the density of states of the neutral fermions. Same sort of thing in the high field metallic state, the conduit metal phase. Now we have a big density of states on the right due to the heavy fermions, the normal charged electrons with a big effective mass. We still have the neutral fermion Landau levels on the left here, and you're getting scattering between them. So this fermions scatter back and forth between the charged neutral states and the heavy fermion metal bands. The scattering occurs, the rate at which it occurs varies as the joint fermion density of states, so it's going to oscillate. And because the neutral quasiparticle density of states oscillates with the magnetic field, so will the conductivity. And so we'll get oscillations in the PDO signal. So that explains why, even though these things, the neutral fermions, the Majorana fermions, are neutral and can't carry charge, they nevertheless influence the charge carrying properties of the system. So here's my conclusion. In the in the low field phase of ytterbium dodecaboride, we have a high thermal conductivity plus a high electrical resistivity plus quantum oscillations. And these things are evidence for fermions that are electrically neutral. And for reasons I explained, because this is a mixed valence system, they're probably Majorana fermions. In the low field phase, the neutral fermions cohabit with a condo insulator. And so there's a little bit of resistance, which these things modulate when they have quantum oscillations. We then cross the boundary into the high field phase, the gap closes, the condo insulator becomes a condo metal. The condo metal has a large Fermi surface, and it's made up of charge-carrying electrons with heavy masses. They dominate the conductivity and the thermal conductivity. But we get quantum oscillations due to the persistence of the neutral fermions, and that also gives us this linear in T resistance. And then in the high field phase, we now have an additional fermion reservoir, this condo metal Fermi surface. And it is now probably a nice place for neutral fermions to go. They don't like to be neutral anymore, and so their Fermi surface starts to depopulate, and that gives us a field-dependent quantum oscillation frequency. So we've got this very strange situation where you have a cohabitation of Majorana fermions with both an insulator with a few electrons in it and the metal with a lot of electrons in it. And these things are actually both new states of matter that have not been identified before. So this is a very interesting time for condensed matter physics, because we have the particle physics influence from Majorana fermions coming in and explaining some of the properties that we're seeing in electrical resistance of things that are insulators, but in all other respects look like metals. So thank you very much. That's the end of my talk. I think you're muted, Pei-Chan.
Oh, sorry. Thanks, John, for giving us this outstanding talk. Do you guys have any question? If you guys don't have a question, I will give you one question. Linear temperature, why you call that the strange metal? It's not possible to be the electron-phonon interaction?
No, the electron-phonon interaction always gives you a much higher temperature dependence. So you get contributions from Einstein-like phonons, which give you an exponential dependence, and then you get something that looks a little bit like a Debye dependence, but they're always higher powers of temperature. So the reason it got christened strange metals is that a lot of the pnictides and cuprates and some of the rutheniates show this linear temperature dependence. And so initially this model by Sakdev's group was to explain that. And what you have to have is some reservoir for the fermions not to contribute to the conductivity. And in the cuprates, they put that down to sort of, they call them quantum dots. And I think they're regions where you have very strong valence fluctuations. And then you have to have that in the same place as a conventional Fermi surface. And you can then get these low energy scattering events, which a density of states argument shows should be proportional to the temperature, and that gives you the linear T temperature dependence of the resistivity. So in our high field state, as there doesn't seem to be any other mechanism that can explain that, we think that that supports the fact that we have neutral fermions and we have charged fermions, and they're scattering between each other. And the neutral fermions are acting as this reservoir which can't contribute to the conductivity, and the charged fermions are the ones that do. And their coexistence gives you the linear T temperature dependence. So there's an interesting thing happening up at about 75 Tesla, and it looks as though the neutral fermion Fermi surface finally depopulates there, and the resistance changes a whole load at that point. But at the moment, we can only get to 75 Tesla because our generator is broken. And so that exploring that might have to wait for a little while.
So, sorry, another question is, then how these linear temperature dependence different than the remember some of the high TC material also at a pretty high temperature has a linear temperature dependence, and they didn't consider that contribute from electron phonon.
No. So the only mechanism that I think can explain this ab initio is this SAC-DEV mechanism, where you have you have the coexistence of fermions that can't contribute to the conductivity in the Fermi surface, and then you have these low energy scattering events between them, which scale as the temperature. And I think that's the only, you know, they tried to explain it using some variant of RVB, but that didn't work. SAC-DEV's model gives a very good scaling. It also, if you put inhomogeneities in it, it gives you a very convincing fit to the magnetoresistance of bad metals like cuprates as well.
Thank you. Anyone has more question? Student, any question? Or even faculty? Oh, I don't know. Wow.
Oh, there we go.
Okay.
Okay, everyone's stunned into silence. Well, if you do need a recording, you know, at some stage, I wouldn't mind giving the talk again and someone recording it. But yeah, anyway, thank you for turning out today.
So how about, is it possible we can have the PDF file of the talk, or this is still too new to be?
Yes, you can. It's very large. So I'll have to do some sort of upload. I can probably send it to you next week when I'm back on site in the lab, if that's okay.
Yeah. We can just post a PDF file. Yeah.
Yeah. Okay. Good.
Huh.
Is Manfred not here today? Manfred Bucher?
Oh, Manfred is not using computer that much, so
okay.
Especially anything Zoom, and he retired for quite a while. So
okay, well, say hi to him from me anyway. So.
Okay, yeah. I will.
All right, well, thank you very much for coming and listening, and I hope I can get over to you in person in the not too distant future. Because as I say, Pei-Chen and I have had some very fruitful collaborations, and it would be nice to get all of that going again. Yeah. Oh, thank you. All right. Well, thank you.
Okay,
Thanks.
Thank you. Then maybe we will call the end of today's colloquium. Okay, yeah. Everybody give John a clap.
Thank you. Thanks very much.
Thank you.
Okay, thank you. Bye-bye.
Bye-bye.